Hello and welcome. My name is Filip Leonarski and I am Beamline Data Scientist at the Paul Scherrer Institute in Switzerland. This presentation continues the journey of Introduction to FPGAs. This module will be about C and C++ high-level synthesis. I would like to start with talking about what is high-level synthesis. Before I go into high-level synthesis, I would like to, however, first talk about traditional FPGA design. Yus was already mentioning this, so just to remind you that traditionally making designs for FPGA or ASIC is done in hardware description languages like Verilog or VHDL. These languages are made to describe electronic circuits with registers and wires. Hardware description languages are in general abstract from a particular hardware choice. So your design in Verilog or VHDL can be synthesized for FPGA or ASIC. Hardware description languages have this option to explicitly describe concurrency. So you can explicitly say that at the same time this and this and this and this operation will happen. And they also have a notion of time. So you can mention when each particular operation has to happen. So hardware description languages give designer a full control over behavior and performance of the hardware design. It's, however, time-consuming to design with hardware design languages. It takes time. It takes knowledge and experience. It is months to verify performance of HDL design. So there comes a question. Is there a way to trade off some of this flexibility and excellent performance of HDLs to actually get better productivity? This is like in software development. The best code, the most performant code, would be written in assembly language for a very particular generation of a CPU. However, it's so complicated that only very short codes are written this way. Most code where performance matters is written in languages like C or C++, but are still relatively low level. They describe memory with pointers, for example. They have a limited number of built-in mechanisms, but they are abstract in a way that a C++ code can be compiled on x86 and on Power System and on ARM system and on multiple other CPUs. But then you can go even more. You can have Python, which is even simpler to use. And even though performance of Python code often does not match performance of C, the productivity for big applications and when fast development is important is excellent. So developer can have a trade-off between the highest possible performance and the highest possible productivity. And yes, this is also available for hardware. So we have a tool called high-level synthesis that allows to describe an algorithm in hardware abstract terms and use this tool to actually generate HDL design of this algorithm based on this abstract description. In a more formal way, we can say that high-level synthesis is a transcompiler from a source language like C or C++ into HDL. It's transcompiler because it compiles one source code into another language source code. But high-level synthesis is not only the transcompiler itself. These are also libraries. It's very often OpenCV for computer vision, Fourier transform libraries, machine learning libraries, and there are also tools, for example, to help with simulation. There are multiple tools available currently on the market to do high-level synthesis. There are tools that come from FPGA vendors. This is from Xilinx and Intel. There are tools that come from companies that make ASIC tools, like Mentor and Cadence. And there are also some academic tools. But in this presentation, I would like to limit myself only to Xilinx high-level synthesis and give you a short introduction of it. So Xilinx high-level synthesis is currently part of a product called Xilinx Vitis, which is a tool set to develop on multiple platforms with a more abstract ways. Before, high-level synthesis was actually part of Xilinx Vivado till version 2020.1, but currently it's only shipped as part of Vitis. Xilinx high-level synthesis supports C and C++. Older versions also support System C, which are extensions to C and C++ that allow better hardware description. But currently, in Vitis, it's only C and C++. It's important if you made your designs in Xilinx Vivado HLS tool, you might have to do some work to adapt it to Xilinx Vitis HLS. There are minor differences. And Xilinx has documentation that helps to port code from one to the other. So what is great that as an input to Xilinx HLS, you actually provide standard C and C++ code. This code can be compiled with modern compilers, like for example GCC or LLVM. What is important to say is that the newer standards of C++, like C++ 11, 14, or 17, have very limited support in Xilinx toolset, so you should be relatively conservative in terms of C++ standard. What is specific to HLS, because in C you cannot actually describe information about the hardware implementation, you can provide this information to the compiler via something called pragma. So in your code, you write #pragma space HLS and then text of the pragma. And this tells the compiler how to optimize the code you have written to hardware. While pragmas that are unknown to a compiler are, according to the standard, ignored. So if you compile your code with GCC or LLVM and it does contain HLS pragma, this will be just ignored. You will not see any warning or error messages. There are two ways to verify correctness of your high-level synthesis code. The first one is called C simulation. In C simulation, your code is compiled by C and C++ compiler into a standard Linux executable, and it's just run on a CPU. The other way is Hdl simulation, where your code is transcompiled to Hdl and is then simulated with tools that are made to simulate HDL designs. C simulation is extremely simple and fast. It is something that is practical to do at the time you're writing your code. You just have an icon in your IDE and you click this icon when you make bigger changes, and you immediately know if you made errors to your code or if everything is correct. What is nice is that C simulation can be paired with tools for automatic testing, like for example Catch2 or Google Test. And then you can run this kind of simulations easily as a part of a continuous integration pipeline. So simulation is a great tool. C simulation is a great tool, but it has limited functionality because it only checks that semantically your algorithm is correct. But it does not check the actual hardware implementation. It does not check concurrency. It does not check performance. And also, important to mention, it does not check whatever the compiler, transcompiler, is doing correct or wrong. It is very rare, but it might happen that code that the HDL generated by HLS tool is not equivalent to what you have written in C. And this has to be checked with HDL simulation. Now, on the other hand, HDL simulation is complex and slow. It can take hours to simulate behavior of your design. But this is much closer to an actual execution of your design on hardware of your choice on the FPGA. It is very thorough. It tests all the aspects of the design, including if there are concurrency problems, like for example deadlocks. It is suitable to do integration tests, but it's rather too heavy for unit tests. Next, I would like to introduce to you some specific HLS concepts to help you start development. Now, this will not be very thorough because the course to learn about all details of HLS by Xilinx takes 2 days, and I only have few minutes. So this is just a starter to give you a bit of feel where to start looking. So the first thing that already Just mentioned in his presentation is arbitrary precision arithmetics. So your CPU can work with numbers of only a given bit width, usually power of 2, like for example 8, 16, 32. Now FPGAs can do arithmetics with any bit width. So you can implement a 5-bit number, a 45-bit number, and a 450-bit number. While on the other hand, your CPU has quite a lot dedicated electronics to handle floating point numbers. While on FPGA, it actually takes quite a lot of resources to implement floating point operations because there is some additional complexity to handle them. So this is something we would like to avoid in the design. So Xilinx HLS tools offer specific types that allow to implement n-bit integers, which will behave the same way as they will behave on the FPGA. So by doing software, this C simulation, you can actually verify that your arithmetics is correct when synthesized on the hardware. It also has a concept of fixed point numbers, which allow to represent fractions, but with a given number of fractional bits. It is simpler than floating points, but is already quite powerful if the range of numbers you are working with is predefined. These types, they have both signed and unsigned versions. In the HLS lab for this course, you will actually be able to play with this arbitrary precision arithmetics. Another concept, very important in working with HLS designs, is pipelining. The way your functions and your loops perform will matter quite a lot depending if you use or don't use specific pragmas. And the one that is most important is Pragma HLS pipeline. In Xilinx HLS, if you write a loop or a function and you do not specify any pragmas, the loop or function will work in a fully serial manner. So first iteration has to finish before the second iteration can start. It's very flexible because the iterations can have a different duration and dependencies can exist between subsequent iterations. However, if you provide special pragmas to tell you would like to pipeline a loop or function in HLS, HLS transcompiler will allow multiple iterations of the loop to start in equal time periods. It allows for much higher throughput, but there are some constraints. All iterations have to be equal in duration, and you have to resolve dependencies before the pipeline happens. Some nomenclature, latency is calling the number of clock cycles for the data to be processed by the pipeline. So this is from the start to the end of this particular data package. So here we see, for example, for the yellow one, it is a time from start to end. Now, during this n clock cycles, additional iteration can start. And this is measured by initiation interval, which tells us that every m clock cycles, a new iteration will start. So if we would like to know throughput, the pipeline, this will be the clock period times data width in bits divided by initiation interval. So if we have initiation interval of 2 with 512-bit data and 200 MHz clock, we can process 6.4 gigabytes per second. But if we would get the initiation interval of 1, then we double the performance and get 12.8 gigabytes per second. So it's always, if possible, to go to get initiation interval of 1. So in certain conditions, pipelining is not possible. This is if subsequent iteration depends on the result of previous iterations. Or if HLS tool believes that this is the case. Sometimes when you work with external memory, actually HLS doesn't know if the dependency can happen or not. And then the compiler is conservative and will not allow pipelining. Then you have to use special pragmas to tell the compiler that dependency is false. It doesn't exist. The other situation is, for example, if every iteration of the loop is using memory I/O, which has limited throughput. So even though the pipeline could take 1 bit of data per 500 per clock cycle, memory can only give data for half of this block. And this will not work. So if you are pipelining aggressively, you also need to ensure that your memories have wide enough interfaces or are partitioned to provide enough throughput. And this is also part of the HLS lab in this course. Now, what happens if you pipeline a function or a loop that has internal loops? First of all, if there is loop inside, it will be unrolled. So instead of implementing this function with a for inside, it will actually do something 4 times. This is sometimes important if you have a loop with very high number of iterations. It will be unrolled and it will end up as a very complex code. So sometimes it's better to avoid this. What is not possible is to use loops that have number of counts, number of iterations dependent on external parameter. Number of iterations is unknown at the time of compilation because this cannot be enrolled. This has unknown execution time and it violates conditions for pipelining. Finally, the main function in the HLS code also requires to define external interfaces. So if you load a variable, do you do a handshake? Or do you load a stream, for example, with axis stream? Or do you access memory with a standard AXI memory mapped interface? However, if you use OpenCAPI and OCAxle, all the interfaces are actually defined in the examples. You just need to copy and paste. So I will not spend time on defining this in details. It's actually quite long reading in HLS documentation. So talking about conclusions, HLS is a great tool to start your FPGA adventure, especially if you are a software developer. HLS helps a lot in productivity, but there are some trade-offs in performance. Understanding fixed point numbers and proper use of pragmas will help you a lot in your adventure with HLS. Thank you very much for listening. If you are interested to learn more, Xilinx has a wonderful documentation about their products. You can go to Xilinx website and read the documentation for more details.